So we can now go for, I just changed it. I just changed it here from linear activation function to RELU, for example. You can see that there's huge impact on the reconstructed image, right? So in this example here, we have activation function is linear function. We will go back to the encoder. We need to, we can use the encoder for dimensionality reduction, and we can use it also for denoising. But it's for this deep autoencoder, I used here linear function. So the activation function is linear function, and the number of inputs. It should be just reversing 128, 64, 32, and this one it will be from 32 to 64, 128, and finally we need to reconstruct this image. So the number of units in the output layer will be 784. So we got the result. So the result will be like this one. So also we still have some reconstruction error, right? So the reconstructed image is not exactly the same as the original image. So in the second slide here, I changed the activation function into RELU. When we changed it to RELU, we got more clean images. So which activation function should we use? This is also a hyperparameter, right? We need to adjust it. It's by trial and error. You need to try. So now we can get better representation of those reconstructed images. So which means as a code, this code, it's more representative in fact. Once the reconstructed images is the same as the input image, right? When it's close, it means this code will be more efficient in fact. It will be more representative. Because coding and decoding, we are just reversing it. In coding, we try to get this reduce the set or the code. And in the decoding, we'll try to use a code for reconstructing the image. So if I can reconstruct a good image, which is close to the original image, it means my code is more representative of my data, right? It's the same size, but maybe numbers is different, right? So the second part here, how can we use the autoencoder for denoising? Denoising is very important because if you are building also machine vision for an autonomous car, so maybe it's dark outside, maybe it's raining. When it's raining, for example, so imagine that I have a camera and the camera takes images, and those images with rain, it will be like noisy images, right? So maybe also it will impact the accuracy of my model. So it will be good idea also to use denoising, autoencoder as denoising. So we can remove all those noise from the image, so we can have better representation of the image, so we can make good decisions. Because light conditions, it will make huge impact on the accuracy of my model. Sometimes you build a system for face recognition, for example, and even with some noise, it will not work. So it will be really a problem, right? So in this case, we need to use the autoencoder as a denoising. And when we need to use the autoencoder as a denoising, it's simple. We will just train it with noisy data, right? So we will have X train, for example. We will add some noise to X train, and the output will be X train without noise. So it's X train plus noise and X train. So it's the same. I train the autoencoder using X train plus noise and X train. The input will be X train plus noise, and the output will be just X train, the clean image. So in this case, we train the autoencoder to reconstruct a clean image from the input image, from the noisy image. So maybe the input is an image in rainy situations, correct, in a dark situation, right? And the output image will be the one which we need to use. So in this case, we can, sometimes you take an image and it's noisy and it's, so maybe face recognition will not work. So if we can use autoencoder for denoising, maybe it will be okay. I'm using images because it's easy to describe it using an image, but it is the same, you are working with a time series, you have some noise. Because we're collecting data from sensors, and sometimes we are getting some uncertainty, measurement uncertainty, noise, and so on. So it will be very, very smart also to try to use autoencoder for denoising. So here, autoencoders are capable of learning new and improved representations from the original data, capturing the most important elements, but disregarding the noise in the original data. So example, imagine recording a conversation between two people at noisy coffee shop, right? If you are using it for text understanding or speech to text, for example, and we want to isolate the conversation, the signal from the background. Sometimes we have some application like this, we are using social robots, and in the social robots, they are communicating with people in verbal way. So if it is noisy, and if the background it's noisy, it will be impossible for the engine to convert the speech into text, clean text, and understand what is going on. So it could be a good idea to use an autoencoder to remove the background noise. Another example, imagine a data set of images that are grainy or distorted due to low resolution or some blurring effect, and we want to isolate the core image, which is the original signal, from the distortion, from the noise. So it's the same application. To design a denoising autoencoder that receives the corrupted data as input and is trained to output the original or uncorrupted as best as possible. So we will just train the model using the noisy images, the corrupted images. So the input will be the image plus noise, and the output will be just the image. So in this case, we will train the autoencoder to try to reconstruct a clean image from. So this is an example. I just used MNest data set, and I added some Gaussian noise. There are different types of noise, in fact. So I just added Gaussian noise, and I trained an autoencoder using a noisy image as an input and the original image as an output. So now I have, this is the original image, and I added any noise to the image. So this is the image plus noise. So I will train the autoencoder using this set. So the input will be the noisy image, and the output will be the clean image. So in this case, in normal cases, if I have an image with a noise as an input, the autoencoder will try to reconstruct the clean image, right? So I had my images. So I have this MNest data set, and I added some noise to it. I just added Gaussian noise to. There are many noise, many different types. There's something called salt and pepper, for example. You can try different types of noise, right? But this is just the Gaussian noise, and I wrote this function for noising those XTrain and XTest, and once we got it, we will use it for training my model. And I defined 4 layers autoencoder. So it's 4 layers. So the first two layers will be the encoder, and the second 2 layer will be the decoder, right? It's supposed to be symmetric, and we need to have in the middle, we need to have this bottleneck. So it will be like this one. I used ReLU, sigmoid, and so the model will have 4 layers. So in the input layer, we will have 784 inputs. It will be reduced into 128. In the second layer, 128 will be reduced into 64. And after that, 64 in the decoder will be, extracted into 128, and 128 will be transferred into 784. So this is my autoencoder, and those are number of parameters which we have. And after that, we will train the model using the noisy image. So just to train. So we need to train the model using, just compile. Maybe it is the code. You need to go to the code to see. We need to compile the model and train the model using the noisy. Maybe you need to go to the link to see the.
Sorry?
Huh?
The video they are still looking at the black box.
Okay, but they have the okay. Yes. So now you have 4 layers. You have 4 layers autoencoder. The first two layers will be the encoder. The second 2 layers will be the decoder, right? And we will train this model using noisy data to reconstruct a clean image from the noisy image. So I trained the model. So now the input, this one will be the input. Those noisy images will be the input, and the output will be this clean image. So I think using the autoencoder also as a denoising, very, very important. You don't need to use it with only images. You can just use it with any segment, with any data, time series, text, for example, and so on, right? Speech. This is very important to remove the background noise, for example, from the speech, face recognition. There are lots of applications where we can use autoencoder. It's also, nowadays, they are talking about those adversarial attacks, for example. Those adversarial attacks, They try to use autoencoder also to train autoencoder using adversarial examples that will try to, protect machine learning from those adversarial attacks. So there are lots of applications, in fact. So you have all examples in GitHub. You just need to go to those examples, try to run those examples, and try to make some changes. Change the model, change the data, try it with a different data set, for example, and so on. I used this one, for example, for MNIST. You can try it with C410 and C400. It's much larger data set, right? C410, it's a data set for image classification, and it's RGB, right? Yes. So it's a three channels, and C410 it has 10 classes, and the C400 it has 100 classes. We have also lots of data sets for face recognition and so on. So it would be really very nice if we can try it with different types of data. It's a home assignment. You have this file, but it's just like this one. It's Olfiti data set. Olfiti data set. It's a data set for face recognition. So you have this file, but it's just only like this one. So the idea here, it's steps. We have some steps. You need to first maybe plot some data, for example, right? We are happy because this one, it's in STK learning datasets. Some years before, we have to work with CSV files and so on. Now it's much easier, in fact, because you can just upload it from STK learn, for example, datasets, and it's already divided into training set and the testing set and the shuffle and so on. So you can just use it from here. So you need to divide the data into training, validation, and the testing, right? Remember to shuffle your data set, because in fact, this Olfiti data set, it's 10 images, I guess, or 20 images for each face, 10 images for each face. It's for a data set for 40 persons. So I guess in total, it's 400 images, 10 for each person. And those 10 images, it has been taken in different orientations, because we build a system for face recognition. So if you want to use a face recognition to get access to the building, for example, you cannot just be in one direction because it will be hard, right? So we just take the image in very different orientations, maybe different light conditions. It's very important. If I need to build a system which can work in any time, in any orientation, for example, I need to train it with lots of images. So we have in this data set, we have 10 images for each face, for each person, and it's for 40 persons. So in total, we have 400 images. So first, you need to divide the data into training, validation, and testing. You need to try BCA for dimensionality reduction, for example. Try to use BCA for this one. I guess each picture here, it's a 64 times 64 pixel. So it's very huge, right? So try to use BCA for dimensionality reduction, and try to reconstruct the image using the reduced set. As Hamad said this morning, for example, we will lose some knowledge. When we use BCA or autoencoder, we will get this loosely reconstructed image, so we will lose some information. So try to do this using BCA, and try to repeat this using autoencoder and make comparisons. So you can try first BCA, principal component analysis, and try, for example, to pick maybe the top 100 principal components, and try to do it also using autoencoder. So the code may be 100, it could be 100, it could be 64, it could be 32, as you want, and make comparisons between autoencoder and the BCA. Try to transfer. Now we have a trained encoder from MNIST. Can you try it here? It could be a good idea, in fact, by the way. Right? Because we trained an autoencoder for MNIST. So can we, because it's data driven, but maybe we can try, right? Is it possible to transfer it into this problem? So we train an autoencoder using MNIST and transfer it into this problem domain and try to reconstruct the image, and we will see. It will be fun because maybe we will get crazy pictures and stuff like this. So it will be really nice to see how the autoencoder will deal with a new data set when it's reconstructed. It will be, because we need to understand transfer learning. Transfer learning is very important. But we use transfer learning in deep learning. We use the first part, which is responsible of feature extraction. We use the feature maps in deep learning. But we can try this one. So can you try it? See? We have the autoencoder already trained using MNIST.
Yeah.
So can you transfer it to this problem and reconstruct this image?
You mean, for example, I have to save weights and
Yes.
something like that for MNIST and use for this?
Use it for this problem, for reconstructing the image here.
I can do it.
Yes, it will be very good.
Okay.
Because we will see
And
how
also
the
I
image.
used for my assignments,
Yes.
but I didn't send for you.
Okay.
Because I sent just one of them for you.
Okay.
Yeah.
It would be nice to try to use the autoencoder and transfer it from one
It's
problem.
possible for use for another example and explain how to use it, not just, for example, this example.
Yes.
Because I have another example. Okay, I can do it.
But we use, usually we use transfer learning for feature extraction, feature map.
Yeah, yeah.
But we can imagine that this one is a feature map, right?
Yeah.
So we will see the construction image, how the construction image will look like, right?
Sorry, this transfer learning usually you said it's used for not dimension, not autoencoder.
No, which for feature extraction. It will be next week.
Yeah.
Next week and the week after.
This is what we use mostly.
Yes,
transfer learning.
when we use a convolutional neural network
Yes.
for feature extraction. But we can try it here for fun. Just to use the autoencoder which has been trained on MNIST for reconstructing images for M50 or CFAR10 or CFAR100.
C410, how to use?
CFAR, CIFAR. I will give you an example. We will have some examples today also. So try to use unsupervised algorithm, right, for this problem. Because it's a classification problem. Can we use unsupervised? Here? We have 40 classes. I mean this or 50, we have 40 classes. We have 40 faces, right?
Yeah.
So can we try unsupervised? We need to try. We will see. We have 40 classes. So we need to use, if you don't want this one, you can try MNIST, because in MNIST we have 10 classes. So can we use unsupervised for classifying? So if you build a system for classifying people and you got a new person, we need really to be able to see if we will be able to classify him. We got a new person, right?
Yeah.
So we need to try some unsupervised learning algorithm. We need to try supervised. I mean supervised at feed forward. Just use feed forward. Or we can use key means cluster, KNN, for example. KNN it's supervised algorithm. So we need to try here KNN MLP, for example. You can try here key C means clustering, right? Confusion matrix, it's very important. When you build a model and you evaluate it, you need to plot the confusion matrix. Very important. You must do it. And you must get type 1 error and type 2 error. Very important. Right? Because this is not something, no one will accept your paper without seeing those numbers. I mean, this is the first thing. Oh, what is the confusion matrix? What are those type 1 error, type 2 error? Call, recall, and precision, and those numbers. Those numbers, you can get those numbers directly from Python, right? So you need to get those numbers. If you are building a model, people are expecting to see those numbers. Without those numbers, they will feel that no, it's non-professional. And so you need to get those numbers, and you need to discuss in your paper those numbers.
Yeah.
After doing this, maybe you trained your model here using holdout validation. Try cross validation, right? Try cross validation. Try stochastic gradient descent, batch gradient descent, and the minimum batch gradient descent. So in fact, in this example, we can summarize what has been done so far in the whole course. Correct? We can just do all. We can try all examples, all tools which we studied. Try feed forward, try key means clustering, try KNN, try stochastic gradient descent, batch gradient, mini batch gradient, hold out validation, cross validation, BCA, autoencoder, right? So just in one example, you can just try all techniques which has been and which we studied so far. And of course, later on, you can add also. You can add deep learning. So you can have an example where you can just show all techniques. Yes, so we finished today for this slide. And do you have any question online? Any question? Okay. So we will start something new. So do you have any question for this one assignment? We have already our assignment, which we are working with those license plates. This one is for yourself. So this is, I mean, like guideline, for example. So when you go home, you can just do this example, try all different models. So you really can check if you know all algorithms. If you don't know something, you just go to the code, go to the slide of that part, and just copy the code from one example, put it here, and make some modifications. In the autoencoder, it's very important to build your autoencoder as a sequential model, and after that, you need to slice it, because I'm interested only in the part which is coding. I'm interested in the code, not in the whole autoencoder. So after training your autoencoder, I need to extract the encoder layers, right? And use it for coding my images. So denoising, try to use it for denoising, for add some noise, because it's face recognition. I don't know what happened in face recognition. It's very complex because orientations, stuff like this. So data augmentation also, and we didn't talk about data augmentation. So data augmentation is very important to extract the size of the data set which you have, right?
And data what?
Augmentation.
Augmentation.
Mm-hmm. So we finished this lecture number 7. I will just close it, and we can. It's deep learning, but we will not start also with deep learning. It will be just warming up. So maybe this is, I mean, we finished shallow learning. So far, all those techniques are shallow learning. We didn't talk about deep learning. In deep learning part, we will not go very deeply. We will just cover CNN, which is very, very important, especially for machine vision and stuff like this. And also we will go for recurrent neural network. Recurrent neural network is very important for text understanding and for time series prediction and stuff like this. And also it's for image as well, especially if you are, tracking objects in a video, for example. So sometimes they have some video, they track someone in a train stations or something. I guess they can track it using RNN, correct? You can track him in different tracks, different frames. Because at the end also the video is a number of frames. Maybe it's 24 frames per second, for example. So at the end it's images. And we can train a model to track a person in different frames, right? And then when we run it, we will be able to track a person even between group of people, right? Sometimes someone did a crime, for example, or something, they track him. Once they got some information from, they train the feature from his body, for example, they can track him in all video. And they can find his path, for example. So RNN also is very important. So we will start with convolutional neural network. Maybe we can spend 2 weeks or something, 2 weeks, 3 weeks in CNN, for example. Maybe 2 weeks is enough. And after that, we can go for RNN. So, but first, what is deep learning and what is, shallow learning, for example? What is deep learning? And we have artificial intelligence, which is more broad, for example. And inside of it, we have machine learning, and after that, we have deep learning, which is a sub-area of machine learning. So AI is the effort to automate intelligent tasks normally performed by human. The definition of artificial intelligence, it's intelligent program, for example, which you can, we try to make a machine which can behave at the level of human intelligence, right? So it is the effort to automate intelligent tasks normally performed by humans. So if we need to, I want to make a decision-making system. I have one who applying for a loan and I want to make decision. So instead of working with numbers, I can just build a machine which can make decisions. So we automate the process, for example. Spam ham, for example, I'm getting lots of emails, and if we didn't classify it, in fact, you will spend lots of time reading emails, which is not important. So you just need to classify it. This one, it's a spam. So you will not get it in your inbox, for example, and you just save your time. And so the field of AI is broad. It consists of, machine learning, deep learning, but that also includes many more approaches that don't involve any learning. So they are not involved in learning, such as what? KNN, key nearest neighborhood. It's an algorithm which is not, it does not learn from data, correct? KNN, right? KNN, it's supervised or unsupervised?
Supervised.
It's supervised. Can this algorithm learn from data?
No.
No, it cannot learn. So it's an algorithm, in fact, which can be used for classifying and stuff like this, but it cannot learn from data. We just need to keep all data with us, and he will make those comparisons, but he cannot learn from data, in fact. So it's an algorithm which does not involve any kind of learning. But key means the clustering, it learns from data, correct? And at the end, we will have centroids. Huh?
During unsupervised learning techniques, you have to learn from data to predict the future.
Yes. So we need to learn from data, but some algorithms, it perform at the same level also. It's a smart algorithms because it can behave at the level of human intelligence. We can classify flowers into 3 different classes, but it cannot learn, right? It uses some techniques and it works with data, but it cannot learn from data, right? Like KNN, for example. This is one example. There is also, expert system. Expert system, it could be role-based system or case-based reasoning, for example. In role-based reasoning, for example, it's based on rules. And we extract those rules from the domain expert. So if you are good for solving any kind of problem, we ask you how do you solve it? And we'll try to break your knowledge into some rules. And after that, build a system using those rules. And the system should behave at the level of your intelligence, for example, the one who provided the solution for us, correct? So if you are buy something from IKEA, for example, and have to monitoring it, for example, so it's a process and it's rules, for example, so you can just build a system to behave in the same way, for example. The one who make decision, you should get loan, you should not get loan, you apply for visa, we will give him positive decision, negative decision, so it's a decision-making process. So they have some inputs, some features, and using those features, he just make decision.
Yeah, you mean whenever we input a new data and we have to, for example, repeat all of computational for this new data that is not learning?
No, it's not learning.
It's like KNN.
Like KNN. Because in KNN, we need to keep all data with us all time, which means we don't learn from the data. If you learn from the data, at some point you say, okay, now I learn it, and I don't need to keep the data with me anymore, right? Because I learned it from data. We adjusted the weights from those. It's a parametric model. We have some parameters, and those parameters has been trained using the data.
I think the majority of supervised and unsupervised learning are not learning.
No, it's learning. It's learning from data. Most of those algorithms, they learn from data.
Because I think we have to, for example,
retrain?
Yeah.
No, it's not. So, we divide the data into a training and testing, and once we train the model and testing the model, so now we are happy with the response, we don't need the data anymore. We can deploy the model, and after that, it will be used for classifying things, and it will just be, so we don't need the data anymore. But if you got a new class, for example, maybe in the future, you need to retrain the model one more time. If you get a new example, a single example, right? So for example, I built a model for face recognition to get access to this lab, and we got a new student. Now, the system now works fine. Its accuracy is 100%. It can classify us, and it can give us access to the building, right? But we got new people next year. We need to get those examples and retrain the model using those examples, so those people can be considered, right? Because the system knows nothing about them. So for example, if I don't have an access to the building, no information about me, the system will classify me as no exit, no entrance, for example, right? But I need to get access. So I need to provide my information to the system, so the system can understand that I'm a person, I'm one of the class which should get access to the building, for example. So it learns from data, we learn from data, right? The one which is not learning from data, it's expert system, rule-based system. We need to extract those rules from the domain expert himself, right? So we need to ask him, how do you solve these problems? So he will say, okay, I compare this number with this number, and if this number is greater than 2, if this one is less than 5, if this one between 5 and 6. So we will extract the knowledge from him as a set of if-then rules, right? And we will use inference engine, and this inference engine will use those set of rules for making decisions. This system does not learn from data. It learns from a domain expert using rules, right?
Yes.
So the problem of those systems, it's static. Once we build it, we have to use it. So I can build a system for a hospital for diagnosis of some disease, for example, medical diagnosis. So we build the system for some disease which are common in Norway, right? Now we need to use the system in the Middle East. In the Middle East, the temperature is much higher, and we have different types of disease.
Completely different.
Completely different. So the system will not work there.
Yeah.
So it will not work. So in this case, we need to rebuild the system one more time. So now it's a system which works, but it's hard to deploy the system in different situations before adjusting the system. If it is a rule-based system, it will be really very expensive for us to rebuild those rules from scratch. It will be very tough. So if we can learn from data, maybe I can get medical journals of patients in Middle East, and the system can learn from the data, and using those data files, maybe we can build a system which can make good diagnosis with high accuracy in Middle East, right? If I want to deploy the system back again in Norway, in South Africa, for example, all what we need is just Excel files and the medical journals, CTR and the MRI scans and so on, and diagnosis by doctors in South Africa, in Middle East, in Norway, for example. So can build a system which can work in everywhere. Because it will learn from data, it will be easy to build a system which can learn from data. But it cannot learn, if it cannot learn from data, it will be impossible to build a general system which can work here and there. It will be impossible. So learning from data is very, very important. So in artificial intelligence, here we have optimization algorithms, right?
Yeah.
Genetic algorithm, genetic
Meta-heuristic algorithms.
Hmm?
For example, meta-heuristic algorithms.
Yes, we have expert system. Could be role-based system, case-based reasoning, right? Case-based reasoning, it means I have someone who applied for a loan and he got the loan. So this is a case which has been classified as positive. I have many cases with different numbers and different features. I have some other cases also which cannot, which has been classified as no for a loan, for example. So I have cases. And if I have someone else who applied, for example, I can measure the distance between him and those cases, in fact. If he is closer to some of those cases, they call it similarity measure, for example. So we can classify him based on those information. So this is case-based reasoning. So case-based reasoning, it's based on the cases. Rule-based, it's based on the experience of the people who are making the decision. So I ask them, how do you deal with this case? This one has this income, this age, this education, this and that. So he can decide, okay, this one will get a loan, this one will not get a loan. So I can extract this knowledge as a set of rules, and I can use this set of rules for making a decision. So it's a human experience. They call it expert system. But in machine learning, we are working with data. And when we are working with data, we should learn from data, right? Which is much easier. But we will have the cost that the system will be black box model. It will make decision. Now we can classify MNIST. But do you know how? We don't know, in fact, because it's a black box model. I mean, we're classifying those flowers, versicolor and those virginica and flower. How the system make it? We don't know. The system is really very complex. In the middle, we have many hidden layers, lots of weights, lots of calculations, right? So we just provide an image, and the system will say, okay, this is versicolor, this is virginica, correct? But how the system make this decision, no one knows. So it's a black box model, right? But you can use an expert system for solving the same problem. So he will say, okay, if the petal length is this within this range, and the petal length and the petal width in this range, for example, this one will be virginica. So if it is a rule-based system, it will be white box, correct? Because it will be easy for us to understand how decision is taken. But today, Machine learning, it's much easier to deal with, to develop, because we have lots of data around us. It's much easier to get access to the data rather than getting access to the people, right? And working with people, because working with people is not easy. It takes time, and once you build a system using role-based, for example, it will be just remain as it is. Maybe we will use it for 5 years, 10 years, and after that, new diseases will come in, and maybe the system mistakes will be too much high. Because it's like doctors. You have a doctor, for example, in a hospital, is not reading anything. He got his bachelor degree. He is working for 10 years. In the first 10 years, his performance was okay, right? And after that, his performance started to go down because he's not reading, he's not updating himself. So it's the same. If we can build a system which cannot be updated, it will be outdated quickly, and we will not be able to use it. But if it is machine learning, once we have any new data sets coming in, we will just retrain the model at any point, and the model will behave very well.
Because for example, I see that case-based, for example, case-based reasoning, to solve it, sometimes we are going to use a time series method, and for using that, we are going to use a deep learning. So everything is like connected with each other.
Yes, I mean, we have those white box models. It's one set of AI, right? And the black box models. Machine learning, it's a black box model, right? Because it's impossible to understand how things are done, in fact. But when it's white box, it's easy to understand, because when they decide that this patient has this kind of disease, we have a technique to trace back and to find which rules has been fired, and I can just study it quickly. I can get a report why he has this disease, so we can get some explanation, in fact. So expert systems, they have what they call it explanation facility. This explanation facility, it traces back which rules has been fired, because when a rule is fired, which means it's satisfied. I mean, the rule consists of it's like input part and output part. When the input part is satisfied, the rule will be fired. Fired means it's active now. So I can find which rules has been activated, for example, or fired, and we can understand why the system said this patient has corona, right? Because but if it is deep learning or machine learning, it will just say, okay, this patient has corona. Why? We don't know, right? Because it's a classification. He will just classify him based on the features. He will be classified him as this cluster, for example. But how this happened, it will be impossible, right? So the field of AI is broad. It includes machine learning, deep learning, but also it includes many more approaches that don't involve any learning, like KNN, for example. Machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. We don't program it, we train it, correct? So it's not, because hard coding is a problem. Sometimes I have been working with social robots, and when we need to do something very quickly, we can just hard code it. But you just use it for one time, right? For one purpose, one reason. But you cannot use it all time. So it's just without explicitly programming those, we can build a system which automatically, nowadays, for example, web programming, for example, when you build website, you can draw it, correct? You can take this image, and the machine learning will change it into the code. So you don't need to make, you learn, web programming, for example, because you can just draw. I need to have this design, you can sketch it, take an image, and the machine learning has been trained to convert this image into a website, a real website. It will generate the code which can generate this. And you just need someone to just go and make some refinement, some small changes to fix it. But it will save you lots of time, right? So it's without programming, right? When we classify MNIST data set, we don't program anything. We just train the model, and the model will do it. Now you are working in this license plates stuff, correct? We are not programming anything. It's not hard coded. We train a model, and the model will make decision. And the system will make mistakes. So I mean, the performance will be sometimes okay, sometimes it will make mistakes, because it's our nature also, because we make mistakes. So if we make mistakes, the model should be also able to make mistakes, right? But we will not hard code anything. We try to train a model to make those stuff. Translation, for example, this computer translations, or It's not programmed. We trained a model to deal with a sequence of text and convert a sequence of text into a sequence of text. So maybe the input sequence will be Noshk, and the output sequence will be English. Correct? So machine learning is a field of studies that gives computers the ability to learn without being explicitly programmed. Deep learning deals with neural network with more than 2 layers. When it's more than two layers, they call it deep learning, right? Because remember, if it is shallow learning, and if you will go too much deep, we will have a problem of vanishing gradient. And vanishing gradient, it's a problem in machine learning. So when you go more deep, maybe you will have this vanishing gradient problem. And in this case, you need to use different types of activation function, like ReLU, for example, rectified linear units, right, to deal with this vanishing gradient problem. Compared to machine learning, deep learning can automatically extract features. I mean, in MNIST data set, what has been done? We can feed it with a raw image, but it will take too much time for training to classify. If you are working with face recognition, or you need to extract some feature, in fact, from the image. Feed those features to the model. But in case of deep learning, we don't do this. In deep learning, we are working with raw images, raw data. So don't worry about feature extraction. We will do feature. We will have some layers for feature extraction, right? You know, I mean, long time ago, people has been using those edge detection filters and in computer vision and in image processing. So we need to use some filters, apply this filter to the image.
In order to extract features?
To extract features.
Also use, for example, genetic algorithms.
Yes. Yes. Can you explain some features? Vertical edges, horizontal edges.
Yes. For example, the corner of top, the corner of left.
Yes.
Bottom.
Yeah, and it was because those filters they consist of numbers. I mean, this filter could be 3 times 3, and it has numbers. So people just inventing those filters. They bought numbers, and they apply convolution for the image.
All of them done and over these days because of the deep learning. Yes.
Now we are doing it using deep learning, and the weights or the numbers of those filters. Because if you open any machine, any image processing book, you can see lots of examples of filters. Each filter has numbers, a size and numbers, right? I mean, those numbers, people from image processing, they put those numbers. For example, -1, -1. If you are interested in the edges, corners, you need to change a different set of numbers. It could be the summation, it could be the average of convolution, multiplying this one by this one. So if you can open any machine vision or image processing book, you can see lots of examples of those filters. It's not that much. Maybe it's a small set of features which we can extract from an image. So if you are working with just shallow learning, we need to do this, in fact. We need to extract some features to make it easy for the machine to make decision, right? But if you are working with deep learning, you don't need to do it. Deep learning works with raw data. And it will develop those filters by itself, right? So we will develop those filters, but the machine will develop, will find those filters. Because, for example, if you are working with face recognition or object detection, for example, in an image, you need to see, okay, I need to find the outer boundaries of this object. When it's curvy, when it's straight lines. So you need to look into the image and you need to decide which filter should we use. We will try different types of filters, correct? So it will take time from you and some experience. But in this case, we just decide the number of filters and it will automatically train it from the image, from the data. It will train the filter. I mean, the numbers inside each filter will be the weight values, which the model will train, in fact, like weight values here. But the weight values here, so for example, I can have an example for a filter. For example, it could be a matrix, it's a matrix, in fact, it's like this one. So for example, if it is for edge detection, maybe they put numbers like this one. I don't know how they put it, in fact. But it's just maybe this one, it's +1, +1, +1. So those numbers, we call it weight values. So in fact, in deep learning, we will replace this one with the same size, but we'll have here weight, omega 1, omega 2, omega 3, omega 4, omega 5, omega 6, omega 7, omega 8, omega 9. Those omega values will be the parameters of this filter. We need to find those combinations. We will initialize it with random values, and after in the training process, we will try to get good numbers. We don't know what numbers we can get. We can print those numbers, right? If it is for vertical edges, we need to get some. If I want to find vertical edges, so in machine vision there are some filters for it. If it is vertical, if it is horizontal, if it is, as you mentioned, something in those corners, so there are something for it, right?
Yes.
So each feature map, there are a filter for it, correct? So in deep learning, we will try to develop those filters. The machine will try to find. You just need to decide how many filters you want. So if it is vertical edges, I need to decide a filter, apply it to the image, and when we apply to the image, we will get a new image, which is a feature map, those vertical edges. If it is horizontal, we will get another one, which is horizontal edges. So each filter will generate a new image. A new image, or we can just call it feature map, right? We call it a feature map. So what is the capacity of us? Maybe to get 5, 6. Because if you open any machine learning book, any machine vision book, you will not find more than maybe 5, 6 famous filters. So there is no big opportunity to get more, in fact. But in machine learning, we can apply a lot. We can just ask the machine to extract 64 feature map, and the machine will learn those parameters. It will find those numbers automatically. We will initialize all those weights with random values, and in the training process, the machine will try to extract as many as possible, and it will try to find the best combination, the most optimum combination of those weights, to extract features which has a meaning for our problem, right? Because now in vertical edges, for example, maybe it has a meaning for us, but not for the machine. So now we will give the machine the freedom to select. We will ask the machine, please extract 64 feature map. Each feature map has a filter. So the machine will find at the end 64 filters. So it will be 64 times 3 times 3. Correct? So this one will be the number of weights plus bias, 64. Correct?
Yes.
So just imagine each filter it's like one each cell, it's a weight value, and each filter, in fact, it's a neuron. So
Yes,
you can just say each one is a neuron, which has 9 inputs, correct? Because this one has 9 weights. So it will be like this one. 1, 2, 3, 4, 5. So it will be something like this one. Correct? And this filter will convolve across the image. It will scan the image.
You use 2 times 3 because of the dimension of filter.
This one?
Yeah.
This is 3 times 3.
3 multiply 3 because of the dimension of filter. Yes.
No, I mean, it's a square, because when it's a square, it's much easier.
Oh.
It's a square because we make calculations and we get the number, put it in the middle here. So it must be odd number.
Yeah.
3 times 3, 5 times 5, 7 times 5, 7.
You use this filter and you add it on top of the whole image. And
Yes.
then you calculate the new value for each pixel, and then you move it, and you use all the values, and then you multiply by all these -1, 0.
Yes. So if you are using a technique from computer vision, you will get some of those filters. Those filters are in all books. But in case of deep learning, in convolutional neural network, we don't do this. We just ask the machine to find those filters, right? You just need to specify the filter size and the number of filters or number of features which you want to extract. And each convolution, we will have a stack of convolutional layers, right? Because we need to repeat this process several times until we get something has a meaning for our problem, not for us, right? I will have some examples today also, where we will have the original image and we will display the feature map. If you can see any correlation between the extracted maps and the original image. So So compared to machine learning, deep learning, you can automatically extract features. A machine learning model transforms its input data into meaningful outputs, a process that is learned from exposure to known examples of inputs and outputs, just a training process. So we will use this training process to get this one. So this is an example. So deep learning is a specific subfield of machine learning, learning representations from data using successive layers to achieve meaningful representation. We will have many layers, right? Because we will have many layers, and also we try to reduce the size of the feature maps, and we will try to, at that point here, we will have some abstract representation of high-level representation of my features, right? Here it's maybe it's low level here, and it will be high level here, high-level features. So the deep learning is not a reference to any kind of deep understanding. When they say deep, it's not in deep understanding like us. Sometimes we study things with deep understanding, and sometimes it's just we scratch the surface, correct? So sometimes we know things deeply, and sometimes it's very artificial and superficial, for example. So deep here, it's not about understanding. Deep about the depth of layers, how many layers. So the deep in deep learning, it's not a reference to any kind of deep understanding achieved by the approach. Rather, it stands for the idea of successive layers of representation using literal layers stacked on top of each other. We have a stack of layers. Deep learning is technically a multi-stage way to learn data representation. We need to learn those data representation. So when we build a deep learning model, it will take care of feature extraction, and it will try to find those nice data representations for the decision process. So this is an example. I have an original input here. So I have successive layers to extract features, and at the end, we will make decision. So at the beginning, we have some convolutional layers, and at the end here, maybe we will have something they call it fully connected layer or dense layer. This is the one which makes decision. Because at the end, I know this MNIST data set will have 10 classes, right? So I just need some layers here to extract some features, and at the end here, I will have a dense layer, which will give me the 10 classes, because I have 10 classes, right? So at the end here, I need to have a layer which give me 10 classes. So deep representation, we will have this example, and we will plot some feature maps. So this is an example. I have some input layer. So for example, here, 1, 2, 3, 4, which means I try to extract 4 feature maps, correct, of the input. So this is the input. This layer, it will transform this one into 4 feature maps. This layer will transform those feature maps into another feature maps. Maybe the size of this feature map will be less than this one. This one, it's a 28 times 28. Maybe this one, it's 26, or maybe the same size. Maybe this one will be less. This one will be less. And finally, I will have high-level representation here of my features, and those features will be used for decision making. Decision making will be done here at the end. So in fact, in deep learning, it consists of convolutional layers, fully connected layer, and in the middle we can have some max pooling and stuff like this. We will. So how deep learning works? It's similar to shallow learning. I mean, there's no big difference. So we will have some input. We will have some data layers for data transformations, stack of layers, another layer for data transformations, correct? Maybe this one it's convolutional layer, this one it's fully connected layer. And after that, we will make some predictions. We have some true targets and the predicted predictions. We will just subtract. We will get a loss function. We will use this loss function for updating my weights, layer by layer, right? Correct. So this is like shallow learning. There is no difference between shallow learning and deep learning in this. Okay, so it's this example, but this example, it's not deep learning. It's not deep learning, right? Because if we need to go for deep learning, we need to start first with just shallow learning. So it's just a model. I can plot it here.
If, for example, in deep learning, it takes care of extracting or dimensionality reduction or feature extraction, then there is no need, for example, to add that in autoencoder and that stuff.
No, we don't need.
Okay.
But maybe you can use it for denoising, for example. right?
If there is no in the image first.
No, we don't need to do this in fact, because we can do this in those convolutional layers. It will extract feature maps. So those feature maps, it will be like the code, because you can consider the code as a feature map. Here we will extract big number of
Hello?
feature maps. Yes.
Please, could you go back to the previous slide?
Yes.
Another one? Yeah, to the layers.
This one?
No, to the layers. The slide where you had layer 1, 2, 3. Yeah. I want to ask, like, the transformation that happens from one layer to the other. How is it influenced by the original input?
Yes, it will change it, of course, because from the original input, we need to classify this one into 4, right?
Okay.
We need to extract useful information from this image. So we need to extract some, how do you call it? Features. Those when we apply a filter to an image. Feature map, is there any other code, other name for it? So for example, if we need to apply, we can apply a filter to this image, for example, and we can extract vertical edges, for example, and horizontal edges, correct?
Okay.
So this one, maybe this first layer, it will try to extract those horizontal and vertical edges.
Okay.
The second layer, it will apply another filter. So this filter will use those features as an input, and it will generate another feature maps, and so on. So we will do this process using a stack of layers, and at the end here, we will have a nice representation of the image. But this representation, we should not expect that this representation makes sense for us. It makes sense for the machine, not for us.
Okay.
So we will have a representation here, which maybe not an image, not anything, but it's something which makes sense for the machine learning model itself. It will help the machine learning model for making a decision much easier.
Okay. And also, in every layer, is the image that is being sent from, for example, layer 2 to layer 3, is it the original input, or layer 2 will refine it and then give a refined image, or each layer just works on the original one? Is there any transformation?
Only layer 1 will work in the original image, only layer 1. And from this layer 1, we will get some feature maps here. Those feature maps will be the input to the second layer. The second layer will apply some transformation, and we will get some new feature maps. So, and so on. We will repeat this process. And the last layer, for example, or the last 2 layers will be something we call it fully connected layers. Fully connected layers, it's just shallow learning.
Right?
But the input will be the features, which we try to extract.
Okay.
This one makes sense when the images are more complex, not very simple. Because for MNIST, we can solve it using feed-forward shallow learning. But it makes sense when the image is really very complex, like in AlexNet. So in AlexNet, you have a vector where there are lots of objects, and I need to detect those objects, and they classify it. So maybe it's more complex, correct? But
excuse me?
Yes.
I have a question. Like, as you mentioned that, for example, if we get the edges in layer 1, then we will feed the layer 2 with those edges.
Yes, correct.
How about the texture and the remaining information? So we will just leave it?
No, I mentioned an example, just an example. So I assume that we want to vertical and horizontal images, for example, but you can decide how many feature maps you want to get from the first layer.
Okay, so we can mention that, for example, we need the edges, we need the texture.
No, you will not mention which feature map. You cannot decide by yourself. It's the machine learning itself. It will decide, because the machine learning will try to. So how can we get those edges, Ahmed? We apply a filter, right?
Yeah.
Can you check online, please, for a filter for vertical images, and can you check? We need to get numbers. Okay. So this one, it's for the x direction. So if it's x direction, -1, -2, -1, 0, 0, 0, 1, 2, 1. This one for x direction. X direction means we were moving in this direction. When it's the y direction, oh, sorry, x, it's like this one. Y, it will be like this one. So in this case, we will get this. It's minus 1, 0, minus 1, 0, 1, 2, 1, 0, 0, minus 2, minus 1. So do you see those two filters?
Yeah.
This filter will extract maybe edges in the x direction. This filter will extract edges in the y direction.
Yeah.
So we have two filters. So if you are working with shallow learning, you need to decide what kind of filters we need to apply.
Yeah.
And you will apply it also in successive way. So I will apply this one first for the image, and after that I will apply maybe this one, another filter, and at the end I will get a feature map which will apply it to the shallow learning. So I will apply many different filters, correct? We will apply many different filters manually to the image, original image, and then we will get a feature map. So just make it, so imagine the original image, it's 28 times 28, we will apply those filters, and at the end I will get a feature map which maybe has the same dimension, 28 times 28. So I will have a single one. This single one, I will feed it to my shallow learning neural network, correct? So it will be like this one, and this one will just make decision for me, right? It will be like this one. So if imagine we have 3 classes, for example, I need to predict, I have an image, and I need to predict, for example, if there is a computer and a chair and a table, for example. So I will apply those features. I did it 3 times, 3 filters, or 4 features, 4 filters, 5 filters, and I will get this feature map. I will use this feature, I will convert all my data into this feature map, and I will use this feature map for training my model. So this is shallow learning.
Yeah.
Yes, but in case, so I will use those feature maps. If you open the book, if you search online, you will get lots of filters, like those filters. This filter, it's a 3 times 3, and it has numbers. Who put those numbers? I mean, scientists, they selected those numbers. They find by trial and error, for example, that those numbers works well, very well, for detecting edges in X direction and in Y direction. In case of deep learning, we don't do this at all. So we will have the first layer, convolutional layer. This layer we will feed the original image to this layer, and we will just decide what is the filter size. So maybe 5 times 5. I will select 3 times 3. So I will say, okay, I need to apply 3 times 3 filter.
Yeah.
How many filters you want? How many feature maps you want to extract from the original image? In this example, how many? We got 3 filters. 5, 6, 10, correct?
Yeah.
So in this case here, in the first convolutional layer, I will decide how many features we want to extract. So maybe I will say, okay, I want to get 64. So in this case, in the beginning of the training process, this neural network, it will initialize 64 filters.
Okay.
So each filter will be like this one. It will be also 3 times 3 because I selected the size 3 times 3. This one will be omega 1, omega 2, for example, omega 3, omega 4, omega 5, omega 6, omega 7, omega 8, omega 9, correct? But I will have 64, 1 from this one.
Yeah.
And we will initialize it, we will initialize all weight values by random values. So how many weights, Hamad, we will get? So it will be 64 times 3 times
plus 60.
No, 64 times 3 times 3. So this is the total number of weights, correct? Those weights are the parameters of the filters. We will initialize all those with random values in the beginning of the training process. And after that, with training, right, those weights will be adjusted, will be updated using delta omega. Remember delta omega? Equal minus eta multiplied by the gradient, the same. So at the end, after training, after finishing your training, you can print out those values. If you want to see what kind of filters my model, my machine learning model has obtained, you will have 64. You will get 64 filters. And then when you apply each filter to the original image, you will get a different map. So at the end, you will have 64 feature maps. Correct? So at the end, Hamad, from this first layer, we will get 64 feature map, new image. One of those was, imagine it was edges in the X direction, one of those whose images, if my model will converge to this one, it will get this one. Maybe it will get different. I don't know how many.
Yeah.
Right? Those invented filters will generate new maps, new feature maps. Maybe Hamad, those feature maps are more useful for the machine, because if we are working manually, I will just say, okay, it looks like edges on X direction works fine. I will use it. Correct? You will select it by yourself. Okay, maybe this one also will help. I will try it. I will try those two filters and I will see this accuracy is okay. Now I'm happy. Maybe I need to add another filter because I feel that there are some information on the corners not counted. So I need to. So you will try to come up with a new filter to try to find a good representation of your images, so the accuracy of your model will increase. This process will done here automatically.
We could set, for example, which section of image we'll use as a filter. Yes, for example, this is an image, and we would like to find a filter from here or here.
No, you scan the whole image.
It's automatically.
No, and we scan the whole image. When we have a filter, we apply the filter on the whole image.
Okay.
Correct? So imagine we got this filter, I will apply it to my image like this one. I will apply it here, it will move with my step stride, as mentioned today, with some overlap. So I will get another image. Right? The size of this image will be less than the size of this image. Correct? Yes.
So that filter is like a kernel, right? So the middle,
It's a kernel.
It's a kernel.
Yes.
so the middle pixel in the kernel is the one for each,
Yes, correct.
part of that.
Yes, it's a kernel.
You look at the neighbors,
Yeah.
and then you add up, you sum up, and then you get a new pixel value.
Pixel in
And
the
then
middle.
shift by one.
Yeah.
You shift by one, you shift by two. So it's a hyperparameter. If you want to shift by one or by two, correct? So it's amount how much overlap you want. If when you are scanning your image, how much overlap you want to keep. Yes.
But we also, if we do it manually, we sometimes use padding to lose some edges. But
Yes.
does it?
Padding, of course.
But does it recognize by itself?
You can decide it. Do you need to have padding, zero padding, or not?
We have to decide.
You need to decide. So if you have really important information in edges, so I need to keep all information, because here we will lose, the size of this image will be less than the size of this image, right? And so we will lose something here, right? We will lose something this, and if you will do this all time, you will lose, there's a first layer, if you have 10 layers, if you have 10 convolutional layers. So if you didn't use zero padding, so each time we will use the boundaries. Each time we will lose the boundaries. So we will lose, and means we are focusing only on the information in the middle of the image. But if there are important information in the edges, we need to use zero padding. It's important because if in machine learning, for example, in autonomous car, just all places are very important, because maybe there is a child who is just crossing the road and he's just coming. So my model should be able to witness, okay, there is a person, maybe he is crossing the road and he is in the corner of in one of the edges of the image, for example. So maybe those information are very, very important.
I think normally if you have a larger kernel, you will lose more information.
Yes,
Because you will start
yes.
so depending on the size of
Yes,
your.
so if it is 7 times 7, we will lose 3 rows, 3 columns from each size, correct?
Yeah, something like that.
Yeah. If it is 3 times 3, we will lose 1 from each. So the size, if the size was, if this one was 28 times 28, and I'm using kernel size 3 times 3, so the input image will be 26 times 26. Right?
This is something that we have to decide. When
You
we
have to
analyze.
decide. So if you need to keep the feature map the same size, we need to use zero padding. And then when we use zero padding, it's according to the size of your filter. You can add 2 rows and 2 column in each side and 2 rows in each side. In this case, the output size will be the same as the input size.
And also whether to use a pooling layer or a convolutional layer. This is also something that we have to.
Yes, you need to decide. I can use convolutional, but it's recommended also to use pooling, because pooling it will try to overcome overfitting, because pooling will reduce the size of the feature map, right?
Full size. in order to pool size.
Yes.
Yes.
So it will, because if you didn't use max pooling or pooling layer, for example, I mean, pooling, it could be average, it could be maximum, and so on. So in this case, we will keep the same feature map size. So in the fully connected, it will be really complex. So maybe you will have overfitting, not in the convolution layers. Overfitting will be in the fully connected layers, right? So, yes. Is it clear, Hamad?
Yes, it is clear. Thank you.
Yeah. So if you decided in the first convolutional layer that we are interested in 64 kernels, correct? So this will be the total number of weights. We will initialize all those weights with random values. And in the training process, the model will learn those values. Each value, each kernel will be in charge of extracting a different feature map. So at the end, I will have 64 different feature maps. So you cannot imagine, does it have any sense for us? We don't know and we don't care. Because the most important for us, it's the performance of the model. If the model will be able to behave much better with those features. The number of feature maps, you need to decide it, correct? So it's hyperparameter. You need to decide the kernel size, you need to decide number of features which you want to extract. We will do this one several times. So in the model, maybe you have a stack of convolutional layers, right? Stack of convolutional layers. And transfer learning, in fact, in deep learning, this is the part which we transfer. We transfer this one which extract features. Because if AlexNet works fine, AlexNet is fantastic deep learning model for object detection and stuff like this. So they have been training it, Google, they trained it using millions and millions of images, big computers, right? So if I need to build a model for classifying images, so I guess it's smart to use this stack, this part of layers on top of your model. So I can use that part for extracting those features because this one is smart anyway. It's the smartest than anything which we can build. So I can just borrow that part and put it on top of my model, correct? For feature extraction and using those feature extraction for making decisions. Mm-hmm. So it will be like this one. Just imagine we have this original image. This is first convolutional layer. From this convolutional layer, we will use those representations. Those representations are feature maps. Number of feature maps, it's up to you. You will select this. It could be 32, it could be 16, it could be 4, 2, 3, 5. So it's up to you to select. But remember, each feature map will be like this one, will be like a neuron. One neuron with 9 connections, right? 9 weights. And of course, if we have a neuron, we will have one bias for it. So we will have this equation of time, omega x plus b. So those feature maps will be applied to the second layer. The second layer will apply new filters and it will extract a different set. It could be 16, it could be 8. So there's no need to be the same number. It should be different or the same. We will have a stack of layers and at the end, we will have, they call it higher level representations of my features or my image. We will use this one at the end for classifying. So this one will be fully connected layers. They call it dense layer or fully connected layer. So the first part, it's for feature extraction. The second part, it's shallow learning, just normal, fully connected layer for decision making. So here in deep learning, we avoid using those manual approaches. We try to automatically extract those features. But in shallow learning, I mean, for the last 10, 15 years, people have been working a lot with machine. You need to study image processing and it's even in machine vision and stuff like this. We don't need to do this now. I cannot, maybe just read a book, for example, to understand how those things work. But in fact, I mean, maybe there is no need to, because if you are very clever, maybe you can apply some features and stuff like this, but the machine will do it because it's the same principle and the machine will be more efficient. The problem here, it's data. You need data. You need a large data set, big data set. So this is the task here, right? We need data to train the model to extract those features automatically and make very good and very wise decisions. So I mean, this is how it works. It's a similar, I mean, there's no difference. Deep learning, shallow learning, both are the same. Name, same way, same approach, there is no difference. This is example, but this example, it's not deep learning. It's just shallow learning. We have here 2 layers, right? 2 layers. So the first dense layer, it has, of course, I mean the input shape will be 28 times 28 because it's MNIST, and the MNIST data set, the size is 28 times 28. So the input size will be 28 times 28. I used ReLU 512. If you are using ReLU, don't scale your data, don't standardize, just use it as it is, right? So we will have this layer. I used here dropout, and the dropout rate it's 0.2, correct?
Yes.
Which means
20% of neurons will be off.
will be off, right? And it's just for why do we need to use dropout?
Maybe because of the improved speed and something like
No,
that.
it's for overfitting, right? Just a way to deal with overfitting. We try to avoid overfitting by adding dropout, and in Keras it's extremely simple, just like this one. It's tough if you need to implement it manually. It will take. It's not a big deal, but also it's much easier here. So the output layer, we need to have 10 classes. So we need to select 10 units.
Yes.
And we use softmax because softmax will give us probability, right? I have 10 classes, so I want to get the probability that this digit belongs to this one, right? So the summation of those probabilities will sum to 1, right? So I'm just, so this is plotting this model. So the input layer, the input layer does not have any parameters. This input layer does not have any parameters. So the input will be 784, output will be 784. First dense layer, output layer, right? So this is hidden layer, and this is dropout. Dropout input equal to the output. There is no parameters. So in dropout, it does not train anything, right? And finally, we have this for decision making output layer. So if you want to find number of parameters, we will have here this number of parameters. This one has 0 parameters. And dropout, we don't learn anything, correct? We don't have any parameters. This is the output. Can you calculate those numbers? Can you get this number?
500.
500.
Times
780.
plus
500.
what? And is this number?
It's 10 multiplied by 784. Plus
Yeah.
10.
Plus 10.
10 plus this one plus 10.
Oh, plus this one.
Yes. Yeah, because this is number of units. It's a 10 times this one
Yeah.
plus this one again,
Yeah. Okay. Yes. Yes.
right? So it's, and I have the confusion matrix for the test set. This is the confusion matrix for the test set. So this is, I mean, this is a simple example, but we need also to do it in deep learning, and we can make comparisons. Can we get better results if we will do it in deep learning, for example? Because I mean, the accuracy here is fine, but maybe it's not the best because we still have, we need to minimize all those numbers in the confusion matrix. We need to increase numbers in this diagonal and reduce all those numbers. What is the meaning of this number? We have 971 0 classified as 0. This one, it means it's 0 classified as 3. This one, it's 0 classified as 4.
Misclassified.
Misclassified. 2 zeros classified, misclassified as 6. Because 0 and 6, maybe it's a close. Here it's catastrophic. 3 zeros classified as 8. Some people, they write quickly, so cannot differentiate between 0 and 8, right? So this is the confusion matrix, right? Confusion matrix is very important. If you are building a model, you must evaluate your model. You must plot the confusion matrix.
And you mentioned about softmax are related to these numbers, yes?
No, I mean the soft matrix.
Yes, for example, 3 is misclassified, and you probably,
yeah, it's a probability.
Yes.
Because the output is probability.
Okay.
So it means, the probability was high that this one was 6, not. So finally, it classified it as 6 and as 8. So I just tried to plot some intermediate values, right? Can we understand anything from those intermediate values? So if the input image is this, okay, this is the input image. This is the output from the first layer, from the hidden layer. This is the output from the output layer. So this one 7, and it was classified as 7. This one 2 was classified as 2. This one it's 0, 1, 2, 3, 4, 9. When it's white, it's 1. When it's 0, when it's black, it's 0, right? So this one it's 7. This is the output from the hidden layer. It does not have any meaning, in fact. Can you see anything here? So for us, it doesn't make any sense. But it makes sense for the model, for the machine learning. So this is the input. This is the output of the hidden layer. This is the output of the output layer, right? So for example, 9 was classified as 9. 9 was classified as 9. 4, it's 4. 0, 1, 2, 3. 0, 1, 2, 3, 4. Yes. So I don't know if we data representation for neural network. I mean, it's just a data. I mean, this one, it's just, it will help us to how data are represented, if it is images, if it is video, if it is stuff like this. How can we represent the data for my deep learning model? I don't know if, maybe I can skip it, for example, but we can take some example. If you have time series, for example, or a sequence of data, so when time matters, the time series is stored as a 3D tensor. Because time, I mean, if I have an images over time, a video is frames. In fact, it's images in frames, images over time. So we can put it in 3D tensor. I guess I can skip this part. Maybe we can go back to it later on. This one, it's a very important data set. It's called IMDb, and it's internal movie database, and internet movie database, IMDb. This one, it's reviews. It's a sentiment analysis, right? Sentiment analysis, which means I have some reviews. People just make some reviews of images, of videos, for example, in internet, and they say this is good, this is positive, this is negative, right? So you can use those reviews to watch new movies and stuff like this. So the input here is text, and the output is, maybe it's 1 and 0, for example. 1 when it's positive, 0 when it's negative. So it's reviews. And I can train a model for sentiment analysis to make those reviews, and I can use it for just, I can train the model, for example, and after that he will classify it automatically if people are writing some reviews about some movies.
This sentiment analysis, because it's an easy algorithm. Okay, it depends on the algorithm, but is it also machine learning? Because I don't see any added value, for example, when using the affine score. I'm using already a model that was built by another guy, and I give him like a text, and it gives me sentiment of that text or a word or something like that.
How did you build it?
It was built by somebody else, like the affine score.
Yeah.
Affine, which is a simple machine sentimental analysis technique.
Is it machine learning also?
This is what I'm asking. This is like it is natural language processing, and they say the model is based on machine learning. But now I'm just applying it because it has kind of dictionary of all the words, and it has already assigned some.
Maybe it's based on statistics. So they try to find the subset. They are looking for a set of words, for example, and if they can't see it, it means it's positive or it's negative.
Yeah.
But I don't know the accuracy. I mean, you don't know.
Is it machine learning?
It could be based on machine learning or statistical models or something. So, but this one here, in fact, it's simple because I have some review. I have a text. Correct, and the text has different size. This is the problem here, in fact, when we are working with text. Because sometimes people ask you to, in a questionnaire, for example, you have a yearly questionnaire by Nikut. So write some comments. Some people write a lot, some people don't write anything. Someone writes one sentence, someone will write a long paragraph, for example. So the problem in text, the size of the text will be different, right? And you need someone to look into it and say, okay, this is positive comment, this is negative, this is positive, this is negative, right? Because because maybe some people are writing reviews about study program and we need to make some statistics. Do they like this study program or not? So we can build a model and the model will count how many positive, how many negative. So it will be easy to quantify it, correct? So if you are providing a service in a bank, for example, and you want to know that, I mean, people do people like it or not? So maybe they will write some comments and it's needs someone to just go through it and they say, okay, this one is positive, this guy, he like us, this one, he does not like us. He criticizes us, supporting us. So sentiment analysis, we need someone to read it and they classify it as negative and positive. And after that, we can train a model, and this model will do this process automatically, right? So you have an article about, for example, newspaper article, and people criticize the government policies and stuff like this. People writing in Facebook, in customer service, sometimes the people just writing comments, and they want to know, is it positive or negative? And it's impossible to do it manually, because you need to get someone who just go through all those, read, and positive, negative, and maybe a person will be biased quickly, right? Because if you have someone who is reading those texts, maybe his judgment will change with time, right? So the idea is to use this text for training a machine learning model, and the machine learning will be able to use. So this one, it's natural language processing, text analytics for binary sentiment classification. Each review is a sequence of words of different lengths converted into a sequence of integers. How can we deal with how machine learning work with text? Machine learning cannot understand the text, doesn't know how are you, right?
They vectorize the
Yes.
tokens.
Yes, we need to convert it into integers, and after that we need to maybe use word embedding, for example, coding. It's similar to the encoder. We need to code the text into a code, correct? And we will use
a token.
Huh?
Every word is a token.
Yes, correct. We will get it into words. We can replace each. We has a list of all words. Maybe it's 10,000, for example. We will replace each word by an integer value, correct? And we can use one hot encoding, but the size will be very large. And maybe after that we can train word embedding, a model for converting this large vector into a code. And we will use this code for training a model, right? So we will have the input text will be this one. This one will be converted into a code, correct? This code will be a list of, or a vector of float values. And each review will have a different code. We will use those code for training a machine learning model. And the model will decide, okay, this one positive, this one negative, this one positive, this one negative, correct? So I have here an example. No, it's just if you want to load the data, you can get this data from Keras datasets.imdb, Internet Movie Database, if you want to get it. You can load the data, you can get word index, for example. So, and I'm selecting the first 10,000 words, 10 most common 10,000 words, because this data set, it's a huge. So we need to decide how many words. So we need to restrict the problem to 10,000, the most frequent occurring words found in the data, right? And we can vectorize, if you want to vectorize, you can vectorize it, which means we are converting each review into a vector of words. So I mean, working with text, it's challenging. This is an example. This is a review, which is a sequence of words. So this is one review. And if we are restricting ourselves to the top 10,000 words, correct? So we will get the review using the first 10 most. So we will skip some words, which is not common. So sometimes when you are reading it, it's not. Does it make sense or not? Because we are skipping some words. Maybe it's full, maybe it's not full. Because we are selecting the most. I mean the top 10,000. So this is the one review. This film was just brilliant, casting, location, so on. So this is one review. We will code it. When we are coding it, we will replace each word with an integer number. We are restricting ourselves to the top 10,000. So now we are just, this will be replaced by 1. Film will be replaced by 14.
Professor,
Pause. Huh?
interrupt. Could you change the camera view?
Yeah, okay. Number 2. If it is an intelligent camera, it should track. We can train the camera to track a person, right? So we have this review. This is one example from this database. This database, it's called internal movie database. Internal movie database, and it's a huge database, and it's used for sentiment analysis of movie reviews. So some reviews are positive, some reviews are negative. When it's positive, it's 1. When it's negative, it's 0. Right? So the output will be probability. Correct? So this is one example. This is a sequence of words. A review is a sequence of words. But remember, the size is different. Right? The size is sometimes it's short, sometimes it's long. Correct? So we will code it. So we will replace each word with an integer value. So for example, here this will be replaced by 1. This is a sequence of words, the most common words. It will be, we will collect, or we will tokenize it. We will get a unique list of words. Tokenization, you know this tokenization process? So we will get a unique list of words, and we will give each word an integer number. And we will just keep the first 10,000 because we need to restrict ourselves, not make it very huge. So in this case, just each word here will be replaced with an integer value. So after that, we will use one hot encoding. So this one, in fact, I don't know the length of this one. What is the length of this one? I don't know. It was better to just count it, right? So this one has a length. The length will be different from one review to another review. Now we need to use one hot encoding. What is one hot encoding? We will replace each one. The one hot encoding, it will be 10,000 10 times 10,000 because we have 10,000 words, right? We have 10,000. We are restricting ourselves to 10,000 words. So we will convert this one into one hot encoding. The size of this one hot encoding, it will be this one. It's one vector. This one vector, right? The length of this vector will be the length of those words. If this one is 2,000 words, this one will be 2,000. But each value will be a number between 0 and 9,999, correct? Total number of words. In one hot encoding, we will convert this one into one hot encoding. And one hot encoding, it's for the first one, for example, it will be 1 when it's 1 and the 0 in the rest. Correct? So this one will be 10,000 times 10,000 values. But it will be binary. Right? It will be 1 when it's in this location and the 0 otherwise. So now we are converting this one into a fixed set. So when we do one hot encoding, all reviews will be converted into this matrix 10,000 times 10,000. Now it's very fine. It's very good. If you want to train autoencoder, what should we do? Flatten it, correct? And you train an autoencoder to convert it into a reduced set. We call it word embedding, correct? Because 10,000 times 10,000, it's crazy. I mean, when you flatten it, what will be the size? 1 million? Correct?
Yeah.
So it will be 10,000 times 10,000. What? So when it's 10,000, no, it will be 100 million. Correct? So when we flatten it, this one, it's a matrix. When you flatten it, it will be one vector of 10 million values. And those 10 million values, it's binary, so mostly zeros everywhere, and it will be 1 when it's 1 and zeros otherwise. It will be 1 when it's in a location of 14 zeros otherwise. So it will be, we will have lots of zeros in this matrix. So you can flatten it, correct, like this one, and you can train an autoencoder to compress it. We can use autoencoder for dimensional reduction, correct? So I can use this one for reducing the dimension. We call it word embedding. So I can just decide, okay, I need to represent this one as a vector of 64 values, but it will be float values. So in this case, we will try to find a code for each review. And the autoencoder will help me to do this word embedding. So now we are reducing it into a code, correct? So anyway, this is a review in words. This is the code where we replaced each word with each word index, correct? Each word here, this one, it's the word index. So 3,785, maybe it's fishing, right? I don't know, maybe 33, maybe it's 2. 8, maybe it's 4.
Why is it 10,000 by 10,000? Shouldn't it be 2,000 by 10,000? The number of words as rows and the number of.
Yes, it will be 10,000 times 10,000. It will be a matrix.
Shouldn't it be 2,000 by 10,000
In
if
what?
you have
No.
2,000 of words?
No, you have 10,000 of words.
Yes.
So how many rows? How many rows? Number of words. It will be from 0 to 9,999.
But that's
Because this is the number of words. And if I want to convert it into one hot encoding, I need also to use the dimension here should be the same size. And it will be 1. So if it is 5,000, no. If it is this one, for example, so it will be 1 here and the zeros elsewhere.
The size is not based on the text, it's based on
Number of words.
how many words
How many
are you
words?
looking for in
Yeah,
the
yeah.
text. So you will probably have a lot of zeros.
Lot of zeros.
A lot of zeros.
Some rows will be just zeros because there is no word from this. I didn't select in this review. Some reviews are long, some reviews are short. But if we will limit ourselves to 10,000, so we guarantee that in maximum, I will have this size, right? But sometimes I will have just some words are not represented at all. So it will be zeros everywhere, correct? And the whole line will be zeros. So this one, it's a very huge, in fact. So if you will flatten this one, it will be 10 million values,
I
correct?
think that why some words are not represented. Why is that some words are not represented?
Because if you are writing a review, maybe I will just write one line, and if someone else, maybe he will write one full page, correct? So I can do a review, for example, say, okay, this movie, I like this movie, I like action movie, that is it. Maybe you are good, you're better than me, you will just write a full page, correct? So some reviews are very short, some reviews are very long. Maybe someone else, he will not write anything, he will shit movie, just 2 words. Right? So it's a negative, but it's a very short. Right? So in this case, we are working with text. I'm working with text. It's more challenging, in fact, than working with any other things, because machine learning cannot understand any text. We don't understand text. We need to convert text into a number. So we can convert it into this sequence, right? This sequence also it's a problem because the size of this one is numbers, but this is a problem because the size here equals the size here. We cannot rely because in machine learning the input size must be fixed. So I need to convert this one into a fixed length. So we use the one hot encoding. There are many ways for encoding. We had discussion before what kind of encoding. One hot encoding, maybe it's not the most efficient way, because we can use binary encoding. It will be shorter, and we can use any different types of encoding. As this is an example, we can use one hot encoding. Now we have this huge vector. This is crazy. If I will use this one, if I will feed this one to a neural network, it will be very crazy because it does not have any meaning, many numbers, maybe it will have only 1,000 ones and the rest will be zeros, right? So we cannot use this one in fact. So we need to use word embedding. Word embedding, imagine it like an autoencoder. So the input to the autoencoder will be this one, and I will decide what will be the size of the code. You can say the size will be 150, 128, right? 156 values. So in this case, I will convert this 10 million values into 128 or 156 or correct values. The code will be float numbers. The code will be float numbers, and each code will represent one review. So after training my word embedding model, for example, I will have also this layer which will convert each review into this vector. And now I have reduced the set of values. I can use it for building the model, which will classify positive, negative, right?
It can work for any language, or
Yes, it can work. Because if it's a Chinese, for example, you can do the job, but you need someone who knows Chinese, and he reads the text, classifies this is positive, this is negative, right?
Because we extract this dictionary from the reviews themselves, so it can be in a language.
Yes.
We have to label them.
Yes, if it is supervised.
Supervised.
Yes, because we need someone to say this is positive review, this is negative review, because it's supervised. But we can do it for unsupervised learning. Why not? if I know that, no, it's, you can try unsupervised because we can classify in more, maybe sad, happy review, sad review, not only positive, negative, abusing. You can find lots of classification, right? Criticizing and so you can define many classes. You can try unsupervised, for example, right? So this one will be the one autoencoding. I extracted this one because I want to show you. I mean the difference. And do you see here? Those are the only. I didn't block all because it's a huge. It's a huge. So I just mark it here in that part where we have ones, and the rest is zeros. And I just selected the one which has ones, in fact, because the majority does not have any values. Right? It's all zeros everywhere. So I just try to mark where we have one. So now we need to build a model for sentiment classification, right? So you can just it's model sequential model. The input shape will be 10. Now I trained it in fact using the integer values, the vector which consists of 10 values. So the input shape will be 10,000, and the output will be 10,000, 1,024 until we have at the end it will be 2. 2 because we have two outputs, positive, negative, right? We use the early stopping, right? I mean, if you want to use early stopping, we need to check the validation loss and the training loss. So we need to watch validation and the training loss, and we plot the model. So the accuracy was 87% with this sample model, and I just used maybe 3 epochs or 4 epochs. So I used only, and how many epochs? How many epochs we? Yeah, compile. Yeah, model fit. I used 25 epoch, and the batch size was 512. And I used a validation set. So in fact, in this validation data, you can select part from the data for validation, or you can just leave it for the model itself to select. You can say validation set equal 0.3, which means we need to use 30% of the training data for validation. So you can do it by yourself. You can provide a set of data for validation, or you can select a portion of your training data for validation. So it's just an example. This is an example just to show you how can we work with text, because maybe in some cases you need to work with text, right? For example, we are working with social robots, and maybe at some point we deal with users. So we need to check if the user is happy, sad, positive, negative. Maybe the user is abusing the robot, right? So the robot will discuss with a patient in a hospital, for example, or a nursing home, and we need to decide if the patient is, treat the robot well or bad, right? Maybe he is, right? So those informations are very important. So you can just collect the text, and you can use one of those models for just say yes, no, positive, negative. And if the patient is positive, maybe the robot can use nice language. If he is very negative, maybe the robot can use abusing the robot, for example, you can use different language, right? So it's a similar example, multi-class classification example from Reuters. It's a Reuters data set. It's short news wires and their topics published by Reuters in 1986, and it's used for text classification. And in this example, we have 46 topics. It's in politics. So we have 46 topics. It's not plus and minus, not positive and negative sentiment analysis, but we have many different topics. It's like in Twitter, for example, you can use Twitter dataset for define what is the most hot topics which people around the world are discussing. Is it politics? Is it oil? Right? So each topic has at least 10 examples in the training set. The data consists of 8,982 training examples and 2,246 test examples. So it's also text. So this is just an example also. So this is one of those news wires. So we have this text. It's the same also. We will select the top 10,000 words, and we will convert this one into this vector, correct? And by the way, I can train the model using this one, or I can convert it into one-hot encoding and use word embedding. If you want to use this one, I know the size of this one will be 10,000. It will be 1 when it's 1. It will be 1 when it's 2. It will be 1 when it's 5, 0 otherwise. So if you want to convert this one into a vector of 10,000 values, it should be possible also, right? So I can just put 1 when it's 19 and 0 otherwise, correct? So I can convert this one into a vector. I mean, in the last example, we didn't use one-hot encoding. We didn't use word embedding. We used the 10,000 vector, right? You have two words of 2 and 2. You will just put 1 when it's 2, correct? So I can convert this one into a binary vector, and I can use this one as an input to my model. Or if you want to use word embedding, so you need to go to something like Autoencoder. So anyway, this is the news. This is coded. We selected the most common 10,000 words, and we replaced each word with each index. This one, it's not 10,000, but the numbers inside here, it's from 0 to 9,999, correct? Which is the index. I can convert this one into a vector, which has a size of 10,000. So it will be like this one. 1, 2, 3, 4, 9,998, 9,999, correct? Right? So, and I will check. So I will look here. We have 1 at 1, so I will have here 1. We have something at 2. We have index 2, so I will put here 1. Do you have 3? No, we don't have 3, so this one will be 0. Do you have 4?
Yes.
We have 4? Are you sure?
4, sir.
We have 4, yes. So it will be 1. Do you have 5?
Yes.
Yes, we have 5. It will be 1. Do you have 9998?
9, yes.
9998. Do you have? No, we don't have, so it will be 0. Do you have 9999? No, so it will be 0. So in fact, I can convert this one into this vector. This vector can be used as an input to my model, correct? And if you want to convert it into one-hot encoding, it's fine. If you want to use this one as an input to word embedding, it's okay, no problem, right? So I can use this one as an input to my model directly, as we did in the last example. We can do the same here also. So the input will be 10,000 values, correct? And if you want to use word embedding, you can use word embedding, right?
This will only count how many verbs you have in your text.
Yes.
It will not be based on the position, on what word is coming first.
First, no,
after,
yes.
and so
Yes.
that's why you're using one-hot encoding
Yes.
to get the structure of the text.
Yes.
They are indexed, yes?
Yes, it's word index.
And for example, we have 2 number of 2.
Yes, yeah, it's a problem.
It's a problem, yes?
Yeah, because repetition, we don't deal with repetition here. So we will just we will put 1 and 2, and that is it, right? But maybe if you are using one-hot encoding, in this case, we can consider this one, right? So this is and this is the output. In fact, this one we have 46 topics. And this one, it's index 3, so the output vector will be like this one. It will be 1 when it's 3 and the zeros otherwise. If you want to convert this one into one-hot encoding, it will be the one in the background here. The one in the background here, it's the one-hot encoding in fact. Do you see it? So the one in the background, zeros, and just one somewhere, this is the one-hot encoding. So it's 1 here and it's 1 here, right? Maybe part of it, because it's very large. So we will train a model. So the model also, the input will be so this model, the input will be 10,000, right? So the input will be 10,000, a vector representing each review, and we have here 128 units. We use the dropout. The second layer, it will be 32. Use the dropout, and finally the output layer, it will be 46 topics.
when you use softmax, then you will get the probability.
Yes,
of,
because
which
yes.
topic it is.
Which topic is it? Because we need the summation of probabilities to be 1. So it's recommended to use, if you will use this cross entropy loss function, I don't know, is it the one which we used here? Categorical cross entropy. Yes. So it's recommended to use something to calculate probability. So we will do this one, and we got something like this one. And this is the training and validation. And we need to look into training and validation because we need to check if we have overfitting. We can see here, do you see? This dots, it's a training, and this is validation, and this is okay, because this is a loss. And at some point, do you see what happened here? Validation increases, correct? So we started to overfit here, right? So in fact, we need to use early stopping, and we need to stop here. We need to stop training here. So when both are decreasing, it's okay, and maybe until epoch number 5, we have
drop out over there, yes?
No, we do drop out. We need to use early stopping. Drop out, it's one way for dealing with overfitting, but maybe drop out alone, it's not enough. So here maybe we need to use early stopping, because if you can see here, so we have a problem here because training is still going down, 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 and validation is increasing. When validation is increasing, it's an indication that we have overfitting. Correct? Because now my model is memorizing my data points as a training set, and it behaves very badly with the validation. So from here, from this graph, we can see that we have here overfitting. Here also, in the accuracy, so this is the accuracy of validation, it goes up. This one also, it's okay until this point. Do you see what happened? Yes. It's a little overfitting, it's not that much in fact. It's not that much. So if we have big distance here, this one is coming down here, we can say that it's a little overfitting. Maybe it's not that much. But it's very important to have this graph if you want to decide if do we have overfitting or not. Correct? Yeah. So, and then when we check those metrics for training, validation, and testing, we have loss, accuracy, and testing. For the testing, it's the loss is this big number. This is accuracy. It's not big difference, in fact. This one, it's higher than this one. So we have a kind of overfitting, but it's not that much. So if you can use early stopping, maybe we can stop here at epoch 10, for example. We can stop here. This is enough. Because if you will keep training your model, it will just start to memorize your data set, and it will not able to generalize. So at some point, we say, no, it's enough. Right? Because you can take an exam. For example, I can give you a few pages. You'll take an exam after 1 month. It's too much. Maybe after 1 day. It could be, if we need to check the performance of someone, we can just say, okay, you have those few pages. You need to study it for 24 hours, and you will take an exam. Maybe he will get B in the exam, correct? But if you give him the same number of data, and you told him you have an exam after 1 month, keep studying all those every day. After 1 month, he will get A. Do you think he is A? Maybe he memorized it, right? He will get A anyway because he has enough time to memorize. But you just need to show it to him, and okay, now you will have an exam. So he will get something which representing his, understanding of the topic, right? His ability, for example. So this is the confusion matrix. So it was shallow learning. It was shallow learning, but those 2 examples are very important because we need to know how to deal with text. We have been working with images, with time series. I have also one good example for time series, maybe for next week. Do you feel tired? You want to take some break? Yes or no? Okay, so we will take. We will start in convolutional neural network after the break, and just take 10 minutes break. Please bring your coffee. But we are very close anyway. We have maybe another 30 minutes.